Now let us learn how a compiler handles array or manage array. So what are the issues that it has to deal with? So for explaining that, I will take an example of simple variable, that is scalar variable. See, in our programs, we use variables as names for representing some data. But when compiler converts into machine code will not have variable names. During execution for this variable, let us say 2 bytes of memory is allocated and the addresses are 100 and 101. Suppose during execution this is the memory allocated. This variable x represents this address and the value 10 has to be stored at that location, means at this address 100. So basically machine code should refer the location with their addresses, not by name. Then compiler has to convert name into an address. When the address can be known, when the memory is allocated. When the memory is allocated during execution. So it means the memory for the variable is allocated at execution, then only the address can be known. Then how compiler will write down the address at compile time. So that's what we will learn about this issue in array, that is a vector variable. Here we have an example array which is already initialized in my program. Then during execution time, memory will be allocated for the array and the values will be stored in corresponding locations. Assume that these are the addresses. Now in my program, if I have written, I want to access a of 3 and there I want to store the value 10. So it means I want to store the value 10 here. Then this statement in my program has to be converted into machine code, which is referring to this address, that is 206. The address is 206. So compiler has to refer to that location, that is 206. So how this code of our program will get converted into machine code? So actually compiler needs address of a location a of 3. So how it is obtained? So at compile time the address cannot be known. So compiler will write down a formula for obtaining the address. So how that formula looks like, let us see. See, this is the name of an array and this is the first address of an array. So this first address we can call it as L0 or location 0. And the name of an array is called as base address of an array. So any location in an array, index in an array can be accessed with the help of base address. Let us say L0. So L0 is the base address, that is 200. So this is the starting address of an array. Then which index I want to access? This one. Its address is how much? 6. So this address I want to access, that is 3 into 2. This gives me 206. So why 3? This is the index that I want to access. Then why 2? Because each integer takes 2 bytes. 2 bytes. So it means from the base address of an array, location 0, I want to access a third index where each index takes 2 bytes. So the final address will be 206. So using this formula, the address 206 can be obtained. So I will convert that into a formula. This is L0 plus 3 into size of an integer. So address of a of 3 is obtained like this. Now for address of any location a of I, how it can be obtained? L0 plus I into index into. Now this is an example of integer array, so 2 bytes. If it is float array, it may be 4 byte, character array may be 1 byte, double array it may be 8 byte. So depending on the data type, the number of bytes taken by each element may vary. So I have to take the size of the data type. So we use a variable that is W. So this is base address, this is index, and this is size of data type. So this is the formula used by compiler for converting any index to an address. Now for obtaining the actual address during runtime, our program must know the base address of an array. So base address of an array will be updated once the program starts running and once the memory for array is allocated. So the address of this location is known during runtime and it is updated at runtime, and it is called as data binding. So if you want to study about this one, you can study about systems programming or assembly language programming. There you can learn about these things. So here we have learned how a compiler generates the formula. So this is a formula for address, and this is not actual address. So this is a logical address. And this is not a direct address. This is related to base address. So this is also a relative address. So the formula is a relative formula based on base address of an array. Some compilers allow declaration of an array from starting index 1 also. Then how the formula will change? Let us look at it. I have modified the declaration. Suppose in some XYZ language, an array can have indices starting from 1 to 5. Then this will be index 1 and the last index will be 5. Now, if I want to access any location in an array, that is A of 3, this location I want to modify it to 10, then how the formula is written by a compiler. So for the address of a location A of 3, the base address, that is 200, plus, see, third index is this one, so it has to reach here, that is 204. So it should be 3 minus 1, 1 less, because the indices are starting from 1 onwards, into 2. So this will be 204. So for any index, address can be obtained by A of I is, this is location 0, L0, and this is index I minus 1 into, this is the word size, that is the data type size, that is a W. So this is the formula if the indices are starting from 1 onwards. So this is not there in C++, but this used to be there in old languages. They used to allow array declaration from any starting index. So programmer can have an array start from 0 also, 1 also. But in C++, it is strictly from 0 only. A reason why? Why in C++ we cannot have array indices starting from 1 onwards? Let us see this. We have seen the formula for array indexes starting from 0 also. So just I will recall that formula, that was I into W. And this is index starting from 1 onwards. So this is the formula. So the difference is there is one arithmetic operation extra, that is minus 1 is extra. So if you count the number of operations, 1, 2, 3, and here there are only 2 operations. So one operation is extra. So as this is an array, for accessing each location, I have to use the formula. So if there are n location, then this operation will be performed for n times if I'm accessing all the locations. So though it's a matter of a single operation, that is just one operation extra, but it will be slower depending on the size of an array. If the size is very large and I'm accessing all the elements, then it will be really slow. It will be affecting the time taken by a program. That is the reason C++ languages, they allow array indices starting from 0 only, because the formula have just less number of operations and it is faster than this formula. So that's all about single dimension array. Now we will learn about two-dimensional array. Let us see how a two-dimensional array is managed or handled by a compiler. In our program, we declare a two-dimensional array like this. Suppose I am declaring an integer type array of dimensions 3 cross 4, 3 rows and 4 columns. Then this is how 2D array we draw on paper. We visualize that this is how we got a two-dimensional array. Any element we can access with the help of its row number and column number. So this is A of 2, 1. But the reality is, during execution, the actual memory allocated will be linear. It will not be in terms of rows and columns, but it will be like a single dimension array. So total 3, 4, 12 locations are there. So here we will have 12 locations of type whatever you have mentioned here. So it's an integer, so 2 bytes I am taking here. Now these are total 11 location, and assuming that the starting address is 200, so on 2 bytes I have increased, and the last bytes address is 222 and 23. Now the problem is how the elements of two-dimensional array are stored in single dimension array. How the mapping is done. So there are two methods of mapping. First one is row major mapping and second one is column major mapping. So these are the two representations of a 2D array mapped on a single dimension array. So we call it as row major mapping or row major representation, column major mapping or column major representation. So we'll learn about both. So first let us look at how a row major mapping is done. Let us look at row major mapping. See, we assume that we have a two-dimensional array and the elements are organized like this. But the reality is they are stored in a single dimension array. How they are stored? So they are stored row by row, row by row. So in row major mapping, the elements are stored row by row. So I will copy these elements row by row. So first row elements are A00, 01, 02, 03. So I will write them here. A00, this is the first value in the first row. 01, 02 and 03. So this is row number 0. This is index 0. So I have completed the first row that whose index is 0. Now I will write down the elements of next row. This is row index 1. Then the last row A20. So this is row index 2. So that's how the elements of that two-dimensional array are mapped on a single dimension array row by row. So this is row major mapping. Now we need a formula that should be used by a compiler for accessing that two-dimensional array. Let us take one example and frame a formula. Suppose I want to access an element at index A of 1, 2. This is the element. A of 1, 2 is present here. Now in our program we will be writing like this, like say A of 1, 2 I want to store the value 10. Then that A of 1, 2 has to be converted in the form of an address by the compiler. So already we know that the addresses cannot be known at compile time. So compiler writes the formula for obtaining an address. So let us observe what should be the formula. So for getting the address of a location A of 1, 2, this ADD is for address. Now to reach here, that is 1, 2, 1, 2, that is present here. To reach here, the starting address is 200, okay, 200. Then I should leave all the elements of one row, that is row 0. I should leave all these elements. So how many elements are there in a row? 1, 2, 3, 4. That is equal to number of columns. So I should leave 4 elements. Okay, 4 elements I have left. Then 200 is this index. If I leave 4 elements, then 1, 2, 3, 4. So here I was in the beginning of the first row. Now here I am in the beginning of the next row, that is index 1. So here, so from here, how many elements I should move further? 1, 2 elements. So I should move further for 2 elements. Then this should be multiplied by, there are 2 bytes for each element because it's integer. So this is 2. So this is 200 plus 6 into 2, that is 212. Yes, I got the address. So I have just worked out by taking the addresses and the index, and I got the address, that is 212. Now let us try for one more element. Let us take this element 2, 3, A of 2, 3. So address of A of 2, 3. So if you see that A of 2, 3 is at address 222. So I should get this one. Now let us follow the same method. First take base address 200. Then from here I should skip 2 rows. So 2 rows means 2 into 4 elements in each row. See, 4 elements and 4 elements. So I should skip 2 rows. Thus I will be in the beginning of this third row, that is row index 2. So it means earlier this was 1 into 4. Now this is 2 into 4 plus. Once I skip first row, I am here. Then I skip one more row, I am here. That I am skipping 4 elements for each row. Then from here I should move by 1, 2, 3 elements. So that is 3 elements. This whole thing should be multiplied by 2. So how much it gives? This is 4 to 8 plus 3, 11 into 2, 22. So this will be 222. So yes, I got the address. Now from these two examples, we are in a position to write a formula for it. So address of any index A of ij, we take I and j for representing the indices. So this is L0 plus, L0 is the starting address, that is the base address, L0, location 0, plus this is I into number of columns. So let us call this as m cross n. So this is n plus this one is 3, third element, so that is j, and this whole thing multiplied by w. So this is the row major formula used by compilers for obtaining the address of elements of two-dimensional array. Two-dimensional arrays are accessed using two indices, but actually they are kept in a single dimension array which needs just one index or the address. So the address is obtained like this. So this is about row major. Now one more thing. See, if a language is allowing indices starting from 1 onwards, then how the formula looks like. So I'll just remove this and show you here. If a language is allowing indices from A of 1 to 3 and 1 to 4, I will not work out everything. Directly I will write on the formula. So the address of any location A of ij can be obtained by L0 plus. See, already we have seen it for single dimension. This I minus 1 was used because the indices are starting from 1 onward. So here it will be I minus 1 into n plus j minus 1 also, then multiplied by word size, that is the data type size. So this is the formula. See, in C++, array indices starts from 0 only. So C++ uses this formula. C language and C++ language follows row major representation and they use this formula. But if any language is allowing indices from 1 onwards, then it has to use this formula. Now when it comes to 2 dimension, let us count the number of operations done. 1, 2, 3, 4. And here 1, 2, 3, 4, 5, 6. So 2 extra arithmetic operations are performed. So this formula will be little slower or costly in terms of time. If you have many elements and the dimensions are very large, then accessing all the elements will be very time consuming using this formula. So that is the reason the languages like C++, they start indices from 0 only. They allow indices only from 0 onwards, so that the formula is little simpler than the other formula. Now next, let us frame a formula for column major mapping. For column major mapping, the elements of this two-dimensional array are mapped on a single dimension array column by column. So I will fill these elements column by column. These elements I will take. So first column array 0, 0, 1, 0 and 2, 0. So first column elements are A, 0, 0, 1, 0, 2, 0. This is column index 0. Then this is column index 1. These elements. So I have finished with these elements. Now these elements. The next column A of 0, 2. This is column 2. Then A of, this is column 3. So the elements of a two-dimensional array are mapped column by column. Now we need a formula for obtaining an address of any element. So this address, I have taken the addresses starting from 200, and as integer, every integer takes 2 bytes. So this is 200 and 201, 202 and 203, 204 and 5, so on. Then let us call this starting address as L0, that is base address, location 0. Now let us take some example element from there and frame a formula. Suppose I want this element 1, 2. See, where is 1, 2? Here. It is in column number 2. So address of A of 1, 2 this is base address, that is 200 plus. Now for reaching this element, I should skip first column and the second column. Two columns I should skip. So 2 into, how many elements are there in each column? 1, 2, 3, 1, 2, 3. So columns are having 3 elements. So that is equal to the number of rows, m, that is 3. So 3, then plus. Once I have skipped column 0, I am here. Then I have skipped column 1, I am here. Now from here, how much I should move? Just one element, one element. So you can see that this is 2 comma 1. So this is 2 comma 1. And this has to be multiplied with number of elements that are W. So this will be 3 to 6 plus 1, 7 into 2, 14. So this is 214. And you can see that the index of A of 1 comma 2 is 214. So that's how we got the address of a given element. Now let us take one more element, that is A of 2 comma 2. Now let us take one more element, that is A of 1 comma 3. 1 comma 3 is here. So how to get the address of that one? So the address of A of 1 comma 3 is 200 plus. Now I have to skip how many columns? I should go in third column. So skip 0th column, first column and second column. So I have to skip 3 columns, and in each column how many elements are there? These are 3 elements. So this is 3 into 3 plus. Now once I reach here, how many elements I should move forward? Just one element. So this is multiplied by 2, and this is 3, 3, 9 plus 1, 10 into 2, that is 20, 220. So 220, this is the address. Yes, 220. The element is here. This A of 1 comma 3 is here. So now we have 2 examples. We can prepare a formula. So let us prepare a formula for any index A of I, j. This is location 0, that is base address L0, plus this is 3 and 1 or 2 and 1. See, 2, 1, 3, 1 are used. So this means first j, then I. So this is j into number of elements in a row, that is 3. Number of elements in a column, that is equal to number of rows, 3. So this is m, plus 1 is taken at the last. So this is I, that is row number. This is multiplied by W. So this is the formula for column measure representation or column measure mapping. I will write down row measure mapping formula also just below this one, so that we can see the difference between them. This was row measure formula L0 plus I into N plus J multiplied by W. So in row measure, I was used first, then J, but in column measure, J is used first, then I. So I can say that in row measure, we go from left to right, and in column measure, we go from right to left. So first J, then I. So first J, then I. In row measure, first I, then J. So this is for row measure, and this is for column measure. Now let us observe one more thing here. See, these 2 formulas, how many operations they are having? Plus, plus, multiply, multiply, plus, plus, multiply, multiply. So both the formulas are having same number of operations. So in terms of time, both are equally efficient. So a compiler may follow row measure mapping, or it may follow column measure mapping. So if you are designing your own compiler, then you have option to select any one. Both are equally efficient. There is no difference in them. We can't say one formula is better than another in any situation. But C++ follows row measure formula. This one, they follow row measure formula. So that's all about that's all about two-dimensional array. We have discussed how row measure and column measure mapping is done, and we have seen the formula for index starting from 0, and also we have seen the formula for indices starting from 1 also for row measure. Now for column measure, you can devise the formula. So you know well that only I minus 1 and j minus 1, minus 1 has to be taken. Then we get the formula for indices starting from 1 onwards. So that's all in this topic. Let us prepare a row measure formula and column measure formula for 4-dimension array, I'll show you the approach. Then using same approach, we will see a row major, column major formula for three-dimensional array also. So here already I have an example of a four-dimension array. Array name is A, data type is something, and the dimensions are D1, D2, D3 and D4. Now, for the address of any location whose indices are I1, I2, I3, I4, then what should be the formula? So let me prepare the formula for row major. In two-dimensional arrays already I have explained that row major is done from left to right and column major is from right to left. So we will go from left to right. So let us take first is I1, the first index, into multiplied by leaving first dimension multiply rest of all the dimensions. So this is a D2 into D3 into D4. Now second index, that is I2. I2 is multiplied by, after dimension 2 all the dimensions should be multiplied. So this is a D3 into D4, dimension 3 and dimension 4. The next is index 3, I3. So the third index I3 after third index. So after third dimension all dimensions should be multiplied. So only D4 is there. Then plus last I4, fourth index. After fourth dimension everything should be multiplied. So nothing is there. So multiplied by W. This is the formula for row major mapping of a four-dimension array. So you might have observed what is the procedure for preparing the formula. So for every index we take the dimensions after those dimensions. For I2 we take all the dimensions after D2. So this is the approach. We have taken it from left to right. Now I will write the formula for column major. Column major formula, address of, now for column major, already I said that for row major we go from left to right, for column major we go from right to left. So let us prepare the formula. L0 plus, first one is index 4, so I4 multiplied by, see this is dimension 4, so take all those dimensions before dimension 4, so D1, D2, D3, D1 into D2 into D3 plus, now this one we are moving from right to left, so next is I3, index 3, so go to dimension 3 and take all the dimensions before dimension 3, so this is D1 and D2, so multiplied by D1 and D2 plus I2, I2 multiplied by, go to dimension D2 and take all the dimensions before that, so that is D1 plus, this is I1 multiplied by W. So that's it. This is the approach for preparing the formula. Using four dimension I have shown you how to write row major formula and how to write column major formula. Now using the same approach we can write the formula for any dimensions, any number of dimensions. So even 2D was following the same approach, but this is a very small problem, so we have seen it thoroughly with the diagrams and everything, but here I am showing you directly the formula. Now based on this formula, by observing this one, we can prepare a general form of this one for n dimensions. So let us prepare a general formula for n dimensions for row major mapping. So I am showing it for row major mapping. Let us take same formula. I will generalize it for n dimensions. L0 plus, see all these terms are added. See this is one term, then next this is the term, next this is the term, next this term. So total 4 terms are there, 4 terms are added. So for addition we use sigma. And here I1, I2, I3 and I4 is used. So I and its subscript, that is I1, I2, I3. So I will call it as P. So P takes the values from 1 to, it is going up to 4. So instead of 4 just make it n. So this will be for n dimensions. So P takes the values from 1 to n, so for n dimensions. So this will become I1, I2, I3, I4 and so on up to n dimension. Next thing, Every index is multiplied by dimensions. This I2 is multiplied by D3 and D4. So it is multiplied by product of dimensions. So this is the product of dimensions, So product of pi we can use of D. Now these dimensions are taking subscript from 2, 3, 4. So this is just 3, 4. So whatever I is, this is 1. So this is 2, 3, 4. So this is taking the values after P. So this is dq, and q takes the values from p plus 1 to n. So it is going from 2 to 4, 3 to 4. So this is 2, so 3 to 4. This is 3, so 4 to 4. So q takes the values from p plus 1 to 4. And this whole thing should be multiplied with w. So this is the rho major formula and general form of n dimension. So similarly, you can prepare a formula for column major mapping for n dimensions. So try this formula by yourself. Now let us do some analysis on this one. I'll remove this column major formula and we'll do analysis on row major formula. Let us see how many multiplications are performed for getting this result. Let us count them. 1, 2, 3. 3 multiplications here. 1, 2. 2 multiplications here. And 1 multiplication here. Then that W is common always. That is plus 1. Depending on dimensions, the number of multiplications inside the brackets may vary. Now for 4 dimensions, how many multiplications are there? This is 3 plus 2 plus 1 for 4D. It means for 5D, how many multiplications will be there? So 4 plus 3 plus 2 plus 1. So for n dimensions, how many multiplications will be there? N minus 1 plus n minus 2 plus goes on to 3 plus 2 plus 1. So this is nothing but n into n minus 1 by 2. So n into n minus 1 by 2 is n square multiplications. Oh, these are too many multiplications. So the time taken for evaluation of this formula is n square multiplication operations. So this is too much time consuming. So the row major formula used by the compilers take order of n square time. So is there any way to reduce the number of multiplications? Let us see what we can do for reducing the number of multiplications. I will take only the portion of formula that is inside the brackets and I will write the formula from right towards left. This is the row major formula. I am just writing it reverse. So this is I4 plus I3 into D4 plus I2 into D3 into D4 plus I1 into D2 into D3 into D4. So I have taken only the portion of the formula that is inside the brackets and I have written from the last term onwards so that we can reduce the number of multiplications. So if you observe, this is having 4 values multiplied, 3 values multiplied, 2 values, and then there is no multiplication. So I have taken from the smaller value onwards. So first is smaller, then go on increasing. Now in this, if you observe, this I4 is as it is plus D4, D4, D4. D4 is common among all these terms. So I can write D4 multiplied by, D4 is common, so I3 plus I2 into D4 is taken as common, so D3 is there, plus I1. D4 is taken as common, so this is D2 and D3. Okay, so I have taken common. So I got one multiplication here. Let us continue and see if we can take more common values. I3 plus. Now in these two terms, D3 is common. So I will write down D3 multiplied by and I2 plus I1 into D2. So I have taken D4 common and D3 common. Now only two terms are remaining here. Further, I cannot take anything common. This formula can be rewritten like this by taking dimensions as common. Now this is the same thing what is there inside the brackets. So let us see how many multiplications are there. This is 1, 2 multiplications, 3 multiplications. Oh, so for 4 dimensions, just there are 3 multiplications. For 4D, 3 multiplications are there. And for 5D, there will be 4 multiplications. So for ND, there will be n minus 1 multiplication. So total time for performing multiplications will be order of n. So this formula reduces the number of multiplication from n square to order of n. So by taking common, I have reduced the number of multiplications. So this is how we can reduce the number of multiplication in row measure as well as in column measure formula. So the rule that we have applied, that is taking commons to reduce the number of multiplication, this rule is called as Horner's rule. So we have applied Horner's rule to reduce the number of multiplications. So that's all with 4 dimension to n dimensions. Now let us prepare row measure and column measure formula for 3-dimensional array. We have already seen formulas for 2 dimension, then I have shown you a general method by taking 4 dimension. Now using the same general method, we will prepare a row measure formula and column measure formula for 3-dimension array. So here I have an example of 3-dimension array whose dimensions are L, M, N, N. Then let us prepare a row measure formula for an element at index I, J, K. So indices are I, J and K. So let us prepare a formula. L0 plus, that is the base address. So I am not drawing a diagram showing you 3-dimensional array. As you know the approach for preparing the formula, same thing will follow. So let us take indices I. This is for the first dimension. So multiply remaining other dimensions. So I into M into N plus second dimension, that is J into, so J is for second dimension, so multiplied by third dimension, that is N plus K, and this was the last dimension, so multiplied by W. So K is the last index. So we have prepared a formula by moving from left to right. Now similarly, let us prepare a formula for column measure representation. So for column measure representation or column measure mapping, address of A of I, J and K, this is, we will prepare the formula by moving from right to left. So this is L0 plus, first take K. K multiplied by, K is for last dimension, so multiply with M and L. So LM we will write L into M. Plus, next index is J. So J multiplied by, J is for second dimension, so take L. Then plus I multiplied by W. That's all. This is a row measure and column measure. This is a column measure formula for 3-dimension array. So I have used the approach that I have shown you for n dimension and I have directly prepared the formula. Now one of the things that mostly confuses the student, that is, see, if I have a 2-dimensional array of dimension m, n, then we say row measure means first row then column, column measure means first column then row. Then if suppose we have 3 dimensions, then what? Row measure means what? So already I have explained this one, that row measure means go from left to right and column measure means go from right to left. Don't say first column then row, because there are 3 dimensions. So if this is row, this is column, then what is this? So instead of giving a name, let us avoid giving any name to that one. Let us say for row measure left to right, for column measure right to left. So that's all about 3-dimension formula.